Hey everybody, thanks for having me. Really excited to be here. Always wanted to come to this conference, but I didn't have a chance to until now, so thanks for hosting. I'm local, nearby, so it's really great. We're going to be talking about patterns and anti-patterns in pattern matching. The agenda, we're going to talk about the before times when there was no match statement. Then we're going to talk about the match statement and when it's not a good fit, when it is a good fit, and when it's a great fit to use in your code. So match is a feature that people have been talking about forever. If you come to Python from other languages, you might be used to like a switch statement or something like that. And you hear this complaint from new Python programmers very frequently, like, where is my switch statement? And they want to have one, and everyone who says, well, if and elif, it's equal, and Python's dynamic, so it's good enough, and blah, blah, blah. But eventually they caved, and they added it to the language in Python 3.10 back in 2021. So it's been around for about 4 years now. I don't think there's a really good set of best practices that have been established for it. You kind of see it starting to show up in code, but I think it's not super familiar to a lot of people. Before there was match, there was all kinds of strange hacks that people would do to get similar behavior. They'd have weird kind of if statements with ternary expressions using Boolean expressions. They would do lookup tables with dictionaries. They'd do weird class hierarchies with command pattern dispatching kind of stuff. And sometimes you even see stuff with the new walrus operator. So it's a great addition to the language, theoretically, to at least end those hacks from happening. So I'm going to start off by talking about when it's actually not compelling, some of the anti-patterns that are kind of non-obvious. So the example we're going to go with is like something that's controlling a car. So there's a car, I've seen all these Waymos around Los Angeles driving around. So this is my small code base starting to have a self-driving AI. So it's going to see the light, whether it's green, yellow, or red, and what to do in those situations. So if the light's red, stop the car. If it's yellow, slow down. If it's green, go. And then it'll raise a runtime error in the case where it's some light color I've never seen before. My code wasn't ready to do that. So it's a very simple if, elif, else way of dealing with this problem. And I can run the code, and I can see very easily, if it's red, then it says stop. If the light's yellow, it says slow down, and if it's green, it says go. So no surprise here. And you might think that this is something that you would want to use the match statement for because it's a very simple pattern. There's a lot of repetition. If you see like if light equals red, and elif light equals yellow, and if light equals green. So there's repetition in there for the equals comparison, and that might be where bugs happen. So it'd be great to deduplicate some of that code and have less of it. This is a toy example, but that's when I think people start talking about the benefits of a dedicated syntax because of the repetition and the possibility of adding bugs. So let's translate this into match. And so on the right in kind of grayed out text is the code you were just looking at. And on the left is the match version of it. And I've inserted a line so you can just see the line by line correspondence. Okay, so it's just really straight port of this. The first thing you'll notice is that the light variable has moved up to the top. So match light, like the value you're trying to match against is only mentioned once. So that's good. You also notice that everything's indented another 4 spaces. So that's, or 1 tab, depending on who you are. And that's harder to read in some ways. And then there's less repetition in each of the case statements. So generally it seems okay. It's a little bit longer, a little bit more indented, but some of the duplication is gone. And it also works, so that's good. So we're off to a good start here. Match is starting to look like something that's pretty good. There's one problem with this code, though, that there's a kind of a code smell here, right? Like string literals showing up in code, that's often a bad sign. You're like, okay, I should put those into constants so that they can be maintained separately, or maybe they have to be translated. Like, usually good not to have string literals all over your code, right? So you'd apply a best practice here saying, okay, I'm going to pull those out and turn them into constants. I'm going to use the constants instead. So here we go. I'm going to define some constants, pretty self-explanatory. And then I'm going to go back into my code that I had before with string literals, and then I'm going to change all the string literals to use the constants. Okay, so this is the same function. Just change those lines to use constants instead of literals. It should work, right? It should work. It doesn't even compile. Syntax error. Okay, so if you've been taught use constants instead of string literals, and you've been taught how a match is supposed to work, you put those two things together and it doesn't compile, it doesn't run. So it's kind of this immediate surprise. So let's figure out why. And so the error seems to indicate there's something wrong with this red line. You know, the capture red makes the remaining patterns unreachable. Don't really know what that means yet, but we'll get there. So let's make a smaller example to kind of reproduce this problem. So I'm going to just take the first 3 lines of code. You see that? So just down to this 3. And I'm going to say, hey, what about this? That's where it says the problem is with red. Can I run this code? And unfortunately, this actually does work. It runs. And it prints stop. So you give it green as a constant, and it will match that, and it will say stop, which makes no sense why that would happen. So now I'm going to write another example, which is just to print it out, because I'm definitely a debug, bless you, I'm a debug by printing person. And so here's my code that adds a print of like what is going on with the red variable that's a constant and the light value variable that's passed into the match statement right here. So there's this red right here and this light right here. I want to know what their values are. Okay? And turns out that the red value has been reassigned to green. It overwrote the constant. And the light value is green as you'd expect because it's being passed in as an argument to the function. But the red constant is overwritten. And it's overwritten just inside the scope of the take debug action function. Just locally in there, the variable shadowing the global one. It's been assigned. So it's a shadowing that's happening. Why does this happen? This is the default behavior of match. So the reason is that what match is doing when you put like a case statement here, like case red, it's not doing an equality operation. It does for literals, but for a name, a variable name, what it actually is doing is an unpacking. So unpacking, also called destructuring, also called like multiple assignment, there's a lot of different names for it, is where you have one tuple and a set of variable names being assigned to another tuple and a set of values of variable names. And so what match is really doing under the covers is saying, hey, I have a variable called red, and I have a value called light from the match expression. Can I assign these two? And if you can assign them, then match is like, yep, those match. So that's the path I'm going to take. And that's the default behavior. So Python is going to look at this structure of a match statement, and it's going to translate it into this code, believe it or not. And that's why red gets reassigned, and that's why red gets reassigned within the body of the function. Everybody get that so far? Okay. Any clarifying question? Okay. All right.
Yeah, I'll get there.
Okay, you'll get there. All right. So now, if you read, what they'll say is, okay, well, you should have been using an enum anyway. That was like a constant, that was just defined in a global. Why don't you use an enum? Because you have a restricted set of values that a stoplight might have, and that's seen as the best practice. So let's go use that built-in library for enums. We define them there. We go back to our code here, and we go through and we replace each of the values now. Instead of the red, yellow, and green constant names, we use a enum class attribute. See the dot in there. And now it works. And so what's surprising is that Python actually uses heuristics to decide what to do. And it looks for the dot. I swear, it looks for the dot. And so if the dot's there, it could be a class attribute, it could be a module attribute, it could be an enum. Then it's like, oh, this has to be something I don't want to overwrite, so do an equality test. If it's not there, then it's a capture pattern, I'm going to assign to it. So this is just like sharp tools, you'll stab yourself with it, you got to be really careful. But one benefit of using enum is you get this nice unreachability exhaustiveness check. If people know, like, in other languages, that it'll fail to compile if you don't have every case in a switch statement. You can actually get that out of MyPy and other type checkers. If you do that, you can even use assert never from the typing module so that at runtime you also assert that, which is pretty cool. So enum, there is a benefit with match. You get some nice like static type checking stuff. But the downside is you get all of this repeated stuff again. So this is now a line longer than the original that was just if-else if. And it's got all this repeated stuff. And so there's really no benefit here. So if you're doing this with match, it's not worth it. When match is good, so let's do a binary tree search. So this is not meant to be an interview question, but let's say we have a binary tree. And there's a value here. Let's say 10 is the value of the node. There's a left side and a right side. Okay. The first value in the tuple is the value. The left is the left side of the tree. The third value is the right side of the tree. So just a really simple nested tuple. And then I have this code that'll traverse it. First, it's like, hey, if my binary tree is just a number, then just do equality. Otherwise, it unpacks the tuple, because it's saying, hey, the tree is actually three things. It's a pivot number, a left side, and a right side. It unpacks them, and it says, hey, there's a value I'm searching for less than the pivot, then go down the left side of the tree, or if it's greater than the pivot, then go down the right side of the tree. So it's just a recursive binary search algorithm. And otherwise, just double check to see if they're equal. They should be, but do that. And so we can run this code. So here's a tree, for example. So this tree on the left, this nested tuple structure, this is what it actually looks like as a binary tree. And we can run some code here on this contains function on just do a for loop. And sure enough, we can see that all of the numbers that we expect to be in here are here. So 7 is in there, 9 is in there, 10, 11, 13, the rest are false. So looks good, it's working. So now let's convert this from if, elif, else into match. Now it's totally different. Look how much less code that is. It's a lot less code, it's a lot more regular. Suddenly this is starting to look pretty good. And let's talk about what's actually happening here, because it's a lot more dense. So this first section is saying, hey, take the tree variable up here that's past the match, destructure it into these three values, the tuple, pull all these parts out of the tuple, and then with it, do some tests. Check to see if the value is less than the pivot. And if it is, then go call the same recursive function down the left side. And the next one is doing the same thing for the right side. And you see this underscore variable, it means like, I don't care what that is, just pull it out, I don't care, I just care about the structure of it. And so match is doing a destructuring and an assignment and a test all in a single line. That's pretty cool. That's what it does. It's super dense. You don't have to repeat a bunch of stuff. And you get the best of all of these kind of aspects. And the last step here, I'm going to go over this in different ways, so don't worry. And the last step here is, in the last case, look, if it's just a tuple where it has a pivot number and the left and right sides are not less than or greater than, then I know it has to be equal. So just do a test. And you get this something called an OR pattern where you can say, do it either way. So you can have like multiple different ways to match a pattern, and you can have one set of code that handles it. So again, it lets you kind of bring a bunch of different structures together into a single code path, which is really convenient. And you'll see that this code works, which is great. Now, typically, you wouldn't use a tuple for this. If you are, that's probably a bad plan. You should be using like a real data structure, let's say, because you're not just doing exploration. So let's say we want to use a class instead. This is going to get more familiar, I think. So we have a node class with a left side and a right side, and we construct a node like this. This would be a lot easier to read, right? You don't have to just like guess at what the tuple is. It's a node with some nested nodes inside of them, each with a value and left and right sides. And now we can look at what would it take to rewrite this using if and elif. It's about the same as it was, a little bit easier because you can see like dot left and dot right and tree dot value. It's a little bit more legible to use a class, so this is better than it was. The tuple destructuring has been pulled out. And now we're going to look at the match version of this. So that's just showing it works. And now we're going to look at the match version. So this is really, really small and easy to read, tight, and so it also works. But it's kind of magical. Like, what is happening here? You're constructing node objects. Like, if you look at some of these things, like right here, this node, like, what is happening there? Am I building an object? Like, what is happening? Well, what match is actually doing, for each of these, it's saying, hey, if I were to try to construct the object this way, would it match the object I have? And if it does, then do these assignments inside of here. So it's like, hey, if taking the tree, if the tree is equal to a node that was built this way, then, so a node that was built with a value equal to pivot and the left is equal to left, then like assign pivot to tree.value and assign left to tree.left, this attribute. That's what it's doing. So it's like, if it were built this way, then pull these values out, please. So it's almost like running things in reverse. It's almost like running the code backwards. And if you've seen pattern matching in other languages, like Haskell and others, it's the same pattern. It's a very similar thing. Like, hey, if you did construct it this way, pull these pieces out. So Python's not the only language that does this. It's a very common structural pattern matching thing. And so you just have to kind of remember that. It's like, oh, the thing on the right side is what's going to be assigned to. And so that's the way to decode this, what's happening. And same thing at the bottom for this, this last part. Hey, if it's a node with just a value, then pull that pivot value out. Okay? And again, we have these guards. These are called guards. They're just if statements that are added at the end that run after the matching has happened. And that makes sure that you can add some extra logic. And it all just runs in order from top to bottom, left to right. There's no special compilation speed ups or anything like that that might happen in other languages. It's just top to bottom, left to right. It does it exactly in the order you see it. Like, does it match this thing? Okay, pull these out, then do the guard statement. If the guard statement matches, then run the code underneath. It's just very straightforward. And I just wanted to reiterate here is that pivot value, you can pull it out multiple ways. Because of this OR pattern, that pipe, it's going to try this one. And if that doesn't work, then it's going to try the next one. And if there's another pipe, it'll try another one. So you can have like 5 different ways you want to try to destructure something, with all of them taking to run the same code at the end, which is really convenient if you're dealing with code like this. Okay, so that's like a good case. So basically I'm claiming that this version is actually harder to read and harder to understand than this version. We could argue about that, but to me it's a lot less repetition. It's a lot easier to see. It makes sense. Now I'm going to show you one more example of when I feel like match really shines. And so, actually, maybe I'll pause for 1 second. I know we're not supposed to do questions, but did anyone have any questions about this spot, just to make sure that everyone understands? Any thumbs up? Hey, one person understands. Anyone else have any questions? Okay. Yes? Is it similar to switching in Java? Yes, in the sense that only one path is taken and the value that's given is only referenced once, this tree up here. But the difference is that with a switch statement in Java, it's like assessing equality or truthiness for each kind of pattern that you're looking at. But here it's actually doing this whole destructuring thing where it's actually like assigning these variable names. So it's assigning this pivot value and it's assigning left. It's doing it all. So it's switch and a lot more. And I think that's why they didn't just call it switch. They called it match because it's really a destructuring and multiple testing all in one. Yeah. Cool. Yeah.
Is this approach like meaningfully less performant than if you just extracted the tuple up front and then just did the if checks?
Yeah, so the question is, how is this in terms of performance? I think it's slower, slightly slower, but it's all about legibility, right? Because if this was your hot path, you would do all kinds of other gross tricks for this code. So legibility first, I think that's what Carol said, right? So yeah, it's good. All right, so let's do the last section here. All right, so this is when match is really marvelous in my view. So let's take a hypothetical situation where maybe you've got some billing software and you've got some customer records stored in JSON. Maybe that was a mistake, but that's what you've got, okay? And you're trying to deserialize them into Python data structures that you can operate on. And so let's say we have some classes that go along with that. I'm going to use the data classes built-in library to do that. And so I've got one for some customers are people and some customers are companies, okay? Those are my two possibilities. The top record one is a person who's a customer, and the second record is an entity, like a company, organization, nonprofit, whatever. And so if I were to write this code normally, I would write it like this. I would have a deserialize function. It's going to load the data from JSON, and then I'm basically going to just kind of walk through the dictionary and like look at the fields. So I'm going to be like, hey, is customer in there? Okay, cool, that's good. Now pull out that inner record, and then I'm going to look inside and say, hey, is both like the first and the last keys in the dictionary? And then if they are, then I can, then I can return a person customer. I can construct that object and I can deserialize from JSON. And then this one, it's like if it's not that, then I'll look, say, is entity inside that inner dictionary? Like, oh, that is, okay, now I can create a business customer, cool. I understand that that's working. And then if none of these cases hits with a return, the last thing is it just raises a value error. It's like, I don't know what this data is. I can't deserialize it. Okay, so this would be an if statement-based way of doing it. And we can run this code and it works. It can print out those values, which is great. And so now let's look at the match version of this. So here's the same thing as a match statement. And you'll notice all of the repetition is gone. Like all of the key accesses, like inner, last, is gone. And the magic here is that there's built-in syntax for dictionary patterns. So it's actually able to destructure and unpack the dictionary, not just one dictionary, but it's 2 levels deep. You see there's a customer, colon, and then there's another dictionary inside of that with last name and first name. It's able to actually like look all the way in and destructure multiple levels deep. And it can do that with lists and sets and tuples and dictionaries and objects. So you could have an object inside of that, and then inside that object, some other objects, and it can go all the way down, which is awesome. So you get rid of all this duplication. It's a lot easier to read, and it's shorter. more maintainable, fewer bugs. So that's great. So in this situation where the data is kind of semi-structured, it really shines. And I just want to talk about, it works. I want to say that. The last thing I want to say was like, what does semi-structured data mean? Semi-structured data is where the meaning of the data can be interpreted multiple different ways. And you often see this in things like object graphs or parse trees. If you've ever looked at an HTML document, that's a good example. There's like 100 different node types on top of each other, nested in with each other. You never know where they are. So it's heterogeneous. To interpret like, oh, what does this tag mean as a child of that tag? You have to understand the context. That's when this really shines. It's great for building parsers. It's great for doing any kind of object graph walking. Anytime you're trying to, like, based on the situation, interpret what the data means, it's really valuable. So match, that's where it really shines. It's semi-structured, heterogeneous data. Great. And so in conclusion, don't use match unless there's really a clear benefit. You might want to feel like you're using every part of the language. Just don't use it. By default, it should not be the first thing you reach for. Only once you've done it as elif, then you're like, okay, I'm doing some destructuring, I'm doing some testing, I'm doing some instance checking. That's when you're like, okay, match could be a good fit. And just be careful of those pitfalls, especially for beginners, because they'll cut themselves. It's good for heterogeneous data, like I said. It's a really deep API. There's a ton of stuff in there. It's more than I could ever cover. You have to read the tutorial's great, PEP 636, but even then you still have to look at the language reference to actually understand all of the options. And that's another thing. It's like once you put this code in your code base, people you work with or other people in open source looking at the code, they're like, what does this mean? So you got to just be really careful about when you deploy it. I would definitely be skeptical of AI writing you match statements. And then the last thing I was going to touch on was this whole thing of exhaustiveness checking. There is some really cool stuff that match can do with exhaustiveness checking. If you read about the typing unreachable kind of guide in the typing library, it'll tell you more about that. You might have heard the Rust people talk about like make illegal states unrepresentable. That's like I feel like a mantra you hear over and over. This is like pretty close to what Python's got in that category, especially around like abstract data types, sum types. So if you've heard those words or have functional programmers telling you about that stuff, this is where you could kind of look and get a taste of what that's like and maybe the benefits for your Python code. Cool. The slides and the code are here. There's a link to my book if you want to read it. And that's it. So thank you.